Welcome back to General Chemistry on Catalyst University. My name is Kevin Tokoph. Please make sure to like this video and subscribe to my channel for future videos and notifications. In this video, we're going to do a simple introduction to Hess's Law, and we're going to work an example problem. So Hess's Law is a common type of problem in thermochemistry, thermodynamics when you get into general chemistry, and you'll even see this later on in physical chemistry if you go that high. And the gist of Hess's Law is you're given some basic chemical equations right here, and they're all associated with this enthalpy right here. Enthalpy is a delta H. So for example, this first reaction, H2 in the gaseous state plus 0.5 of O2 in the gaseous state yields water in the liquid state. And the enthalpy associated with this reaction is negative 285.8. And I don't need to read all of these. I think you get the idea. Each reaction has an enthalpy. Now, whether or not the question states this explicitly, what you're asked to do is really derive this equation down here. It says, from the above equations, derive this. Now, in general, the question will ask you to calculate the total enthalpy of this reaction right here using these three equations. However, to calculate the enthalpy of this, you have to sum these equations in some way, add them together in some way to where they add up to this chemical equation right here. Now, when you're first doing these problems, that's easier said than done. But let's talk about some strategies that we can use to do that. First of all, this equation that you're asked to derive, I've often called the master equation. Master equation, because we've got to somehow get these three equations over here, put them in such a combination that when they add together, they'll get this. And we'll talk about how that occurs in just a few minutes. Okay? Now, things we can do. We can double the reaction. Okay? That will double the enthalpy. Now, this might seem a little bit weird to you, but just bear with me. So let's suppose I have a reaction where A goes to B. I could easily just have that as oxygen goes to water. Okay? These are just chemicals. A goes to B. And let's say the enthalpy associated with that reaction of A to B is 100 kilojoules. If I double the reaction, that just means whatever the coefficients are in front of these chemicals, I just double them. So these are both understood to be 1. So instead of 1A to 1B, we now have 2A to 2B. That also doubles the enthalpy. So instead of just being 100 kilojoules, now the enthalpy is 200 kilojoules. If I double this one right here, I'd have 4A goes to 4B, and now I'd have 400 kilojoules. Hopefully that makes sense. You can also triple the reaction. You can quadruple it. If you triple it, you have to multiply everything through by 3. If you quadruple it, everything through by 4, and so on and so forth. I can also reverse the reaction. So for example, instead of going C to D, I could reverse it from D to C. Now this C to D reaction has an enthalpy of 200 kilojoules, let's say. If I reverse this and go D to C, I have to reverse the sign of the enthalpy. So instead of being positive 200 kilojoules, it would be now negative 200 kilojoules when I reverse it, now going D to C. If I took this again and reversed it back to C to D, well, I would reverse the sign of this negative 200 kilojoules, and it would go back to being positive. So reversing the reaction just flips the sign of the enthalpy. So it either goes positive to negative, or if it's already negative, it goes to being positive. And then I can have some combination of these. So if I have a reaction of E to F, that is 1E goes to 1F, and the enthalpy is 100 kilojoules, well, now I have this, 3F goes to 3E. Well, clearly I tripled everything, so I'm going to triple the value of the delta H. Instead of 100, it's going to be 300. However, notice I also reversed it as well. So instead of being 3E to 3F, it's 3F to 3E. And therefore, not only do I have to triple that delta H to 300, I have to flip the sign of it to being negative. And if you get these three rules, well, you're on your first step to really solving a Hess's Law problem. Now, essentially what I'm going to have to do is I'm going to have to add these equations in such a way like this to where certain things are going to cancel out, and then I'm left really with this bottom equation right here, which is the master equation shown up here. That's what we're going to work on right now. Okay? So let's actually start looking at a strategy to complete this. Okay? Now I know the phases aren't written here, but the carbon is assumed to be graphite, the hydrogen assumed to be gas, the CH4 is assumed to be a gas also. Okay? But in reality, to do this, you'd have to make sure that the states of these matter line up. So the first piece of strategy that I'm going to tell you to do is look at the master equation and go chemical by chemical by chemical. We're going to first look at carbon, which is in its graphite state. So looking at that carbon, which side of the equation is it on? Is it on the right side or the left side? Well, it's clearly on the left side of the equation. So I'm going to go up to these ones over here and find that carbon. And I find it right here in the second one. And I ask myself, is it on the correct side of the equation? Well, if it was on the right side over here, we'd have a problem, because it's on the left side down here and it would be on the right side here. However, in our example, it's already on the left side, so it's on the correct side. That tells me this second equation I am not going to need to change at all in terms of its direction. I'm not going to need to reverse it. The other thing that this tells me is the coefficient in front of this carbon in the master equation is assumed to be 1. This coefficient is also 1. So not only do I not need to flip it, I don't need to multiply this equation by anything. So this second equation right here is really good as is. I'm just going to bring it down right here. Okay? So carbon in its graphite state plus oxygen in its gaseous state goes to CO2 in its gaseous state. And I'm just going to bring that delta H right down, negative 293.5 kilojoules per mole. All right, let's go to the next chemical. And by the way, you don't have to do this in order. But I'm going to do it in order for now. So I see 2 H2s, so 2 hydrogen gases. I'm going to look up at these equations right here, and I'm going to see, do any of them have hydrogen gas in them? Well, the third one does not have hydrogen gas. The second one doesn't. We already kind of said this one was good, so we don't even have to look at that one, most likely. The first equation right here does have hydrogen gas. Now, the question you should ask first, is it on the right side, I should say the correct side of the equation? Well, in this master equation, it's on the left side, right? Not on the right, it's on the left. Up here, hydrogen gas is also on the left side, so I'm not going to need to reverse this reaction. But is the coefficient the same? Well, in the master equation, it's 2 H2s. Up here, it's just 1. So what I'm going to have to do to this first equation is I'm going to have to double it, okay? And when I double it, this H2 in the gas is now going to be 2 H2 in the gas. This oxygen, which is 0.5 or half an O2 in the gas, is just going to go to 1 oxygen in the gas. All right? And then the water right here in the liquid state is going to get a 2 in front of it, 2 H2Os in the liquid state. But remember, I also have to take this delta H, negative 285.8 kilojoules per mole, and multiply it by 2. Everything has to be doubled in that case. So we'll actually calculate this on the next slide, but it's going to be 2 times negative 285.8 kilojoules per mole. All right. We have one more thing to look at here in the master equation, and that's methane, or CH4. It's also in the gaseous state. Now at this one, I have to find out, first of all, which side of the equation is it on? Well, it's on the right side. So I need to look at these equations and see if, first of all, it's on the right side. Well, the only one up here with methane, or CH4, is this third equation, but is that methane, or CH4, on the correct side? And the answer is no, it's on the left side. So that tells me that I need to flip this equation. And so to flip it, I'm just going to reverse it. I'm going to put these two products over here as reactants, and then these two reactants over here as products. I have that shown down here. So I'm going to get 2 H2Os in the liquid state, and I flipped it, plus CO2 in the gaseous state, goes to CH4 in the gaseous state, plus 2 oxygens in the gaseous state. Again, notice everything has been flipped, but I don't need to multiply it by any number because there's 1 CH4 here, there's 1 CH4 here. Okay? Coefficients are correct for that. But I do need to reverse it. And so when I bring this negative 890.4 kilojoules per mole down, I'm going to have to throw a negative sign in front of it, which will allow me to flip the sign of it. Now, essentially what I'm going to do from here is I'm going to just calculate all this stuff and add it up. And that's going to be my total delta H of this reaction right here. But before you do that, there's an important step that you really should do. You actually need to see if you can cancel some of these chemicals, okay? Because notice, in these reactions, I have oxygens here, right? But in this master equation, there's no oxygens. So somehow these oxygens must cancel. And the same is true of some of the things like water. And the way that you cancel is if you have something on the left side of these equations, so to the left of these arrows, okay, you can cancel it with something equal on the right side of these arrows. So let's do the simplest example, carbon dioxide. Here in equation 3, I have a carbon dioxide, CO2 in the gaseous state, on the left side of the reaction arrow. Up here, I have a CO2 in the gaseous state on the right side of the arrow. So because I have two equal things on either side of the arrow, exactly the same, even the state has to be the same, I can go ahead and cancel those CO2s. Okay? If I'm looking at the waters, here on the right side of the equations, I have 2 H2O in the liquid state. Over on the left side of the equations down here, I have 2 H2O also in the liquid state. So again, these waters can cancel. So again, that state of matter is important. If this one were a liquid and this one were a gas, they technically would not cancel, even though it's both H2O and the coefficients were the same. Okay? Everything has to be the same. And then for the oxygens, here on the right side of the chemical equations, I have 2 O2s in the gaseous states. Here I just have 1 O2 in the gaseous state, but then there's a second 1 O2 in the gaseous state over here. So 2 of these on the left side, so there's 2 of them there. 2 O2s in the gaseous state right here, so they completely cancel. And you'll notice everything that's left over is really just what's in my master equation. I've got the carbon in the graphite state, plus 2 H2s in the gaseous state, and then go to CH4 in the gaseous state. And so when you do a Hess's Law problem, yeah, all of these strategies are important, but again, you want to make sure that everything cancels appropriately before you start adding these up. But everything canceled appropriately. Now we can add these up and get the total delta H of this reaction right here. And so the way we're going to do that is we're just going to sum these up. So I'm first going to take that negative 293.5 kilojoules per mole. That's right here. I'm neglecting units there. I put them at the end. Then I'm going to add on 2 times negative 285.8 kilojoules per mole. So I'm going to distribute that 2 and double that. And then I'm going to add on a negative 890.4. These two negatives will cancel and give us a plus sign. And so again, when I simplify this, I get negative 293.5 minus 571.6. Again, this is minus this number because I doubled 285.8, but I had to include this negative sign there. So it's minus 571.6, and then minus a negative 890.4 is as good as plus 890.4. And then everything is in units of kilojoules per mole. And when I add these together, we have a delta H of reaction of 25.3 kilojoules per mole. So this is actually an endothermic reaction because our delta H is positive. Endothermic meaning that this system is actually going to absorb heat. It's going to take in heat and most likely increase in temperature as a result. Okay? So that is a full Hess's Law problem. Obviously, when you're first learning this for the very first time, it's very imposing, and it might take you some time to really get through the problem. It's going to take some practice. But my biggest tip going forward with a Hess's Law problem is don't try to just add these up, okay? Get a strategy going. What you need to do is look at the master equation, go chemical by chemical, and ask yourself, is that chemical in the equations up here, is it on the correct side? If not, reverse the reaction. And if it has the wrong coefficient, well then multiply it by something, and then remember to do the same things to that enthalpy. And then kind of write the equations as you go like this with the associated delta H's, and then you can cancel them to make sure that you added things up correctly. Because when you cancel everything as appropriate, you should be left with simply the master equation. Then just take all the delta H's with their modifications, add them up, and you have a total delta H of reaction. So that is Hess's Law. We'll do some more examples in future videos. Please make sure to like this video and subscribe to my channel for future videos and notifications. Thank you.